Welcome, everybody. I'm Robert Massey. I'm from the Royal Astronomical Society. It's my pleasure to welcome you here today to this latest in our series of public lectures. You'll be aware that we run these throughout the year, and it's always our pleasure to bring people in to see so many of you today. And I know also there's, I think, a couple of hundred people watching online as well. So we'll take questions through that route too. Over the next, I guess, 3/4 of an hour or so, we'll hear this talk, and there'll be a chance to take questions at the end, or to put questions at the end, rather. I also have to give the predictable fire safety announcement. If you hear the fire alarm, obviously we will leave the building. We'll go out via the main entrance. In the unlikely event that was blocked, it's only just there. There is an alternative through the basement as well, and we'd obviously escort people out. And rest assured, we'll be leaving if that happens, so you'll know it's real. No fire drills are scheduled. But to turn to the substance of today's meeting, it's my great pleasure to introduce Alexandra Amon, who is an expert in cosmology, which is very appropriate given the topic of her lecture. She's a Senior Kavli Fellow at the Institute for Cosmology and a Senior Postdoctoral Researcher at Trinity College, Cambridge, and her career has encompassed places like Stanford and SLAC. She got a PhD from the University of Edinburgh just back in 2018. I should mention, although it's not on the biog online, she also won our Winton Award last year for outstanding work in research. And this year, and part of the reason she's here today is that she also won the Caroline Herschel Prize Lectureship. So, an extremely distinguished speaker, enormous accomplishments already in her career. And it is my great pleasure to introduce her and hear about Unveiling the Dark Universe with the Dark Energy Survey. So over to you, Alex.
Okay, it's really great to see you here, and good to see so many of you in person. It's always better to have people in person than just hearing the number of people online, so I can see actual faces. My job is to study the invisible. So I co-lead a large international team to survey our night sky and to harness the information from our cosmos. And with the images we take, we make measurements, and we use them to try to answer the big questions. So cosmology asks, what's out there? What is our universe made of? Why does it look the way it looks when we peer through our telescopes? And how did it get to be this way? How did it evolve? And the beginning and ending of the answers to those questions is dark matter. Now, my team isn't the first to ask these kinds of big questions. We go all the way back to ancient civilizations, and they've looked up at the night sky and wondered these grand ideas. And we humans can be proud, I think, that we've honed we've come so far with our understanding. We've honed a standard model for cosmology, and it does a pretty remarkable job at describing all kinds of observations. And yet, as I hope you'll see by the end of my talk, we also have a long way to go. And I think what's really special about cosmology is that it has a history, like no other field, in my biased opinion, of turning our views totally upside down. So it has a knack of defying our expectations and altering the way we view our place in the universe and our existence. And to me, that's the most exciting prospect of my work. So let me show you a couple examples of what I mean to get us started. So the first time we had, the first blow that I'm going to talk about for our field came from Einstein and Eddington. So Einstein rewrote our understanding of gravity, the very law that governs everything we know. And at the time, scientists were pretty content that if I was holding an apple and I let it go, it would hit the floor, or that if I threw a ball across the room, we could predict exactly the speed and location it would land on the other side. We really thought we understood motion governed by gravity. And that makes sense because Newton's laws of gravity had held up to all the observations that we were making on Earth. And only when we started to look further afield at larger distances and more extreme environments did we start to see this law break down and cracks coming up. For example, Newton's law can't explain the orbit of Mercury perfectly. You need something else. And so Einstein proposed this new theory, general relativity, and really think about it at the time. He was like, no, we don't understand this. We need a new law of gravity. It would have been totally mad. So his theory proposed that any object with a mass, whether it's a planet or a galaxy cluster, would distort the very fabric of our universe, space-time. So as a result, that means that light from faraway galaxies, as it travels across space-time, their light path would get bent due to these distortions. It would trace the distortions. And because of that, he claimed that if there was an eclipse we would be able to see stars that actually lived behind the sun because their light would be bent due to the mass of the sun. And you need an eclipse so that it's dark. And so, you know, Eddington set out on expeditions to try and test do this ultimate test of his theory. And of course, what he found was that it proved the theory right, and Einstein's theory of gravity still stands today. Yet here are the New York Times headlines at the time. So lights all askew in the heavens and men of science more or less agog. You know, while general relativity is the bread and butter of an astrophysics degree today, back in 1919, it really was a blow to the way we understand our universe. Now, we had another shakeup for our understanding of the field coming from Vera Rubin and the observations that she made. So they really forced us to pause and rethink our progress and think outside of the box. And I'm not just talking about the fact that there's a woman doing science in a dress in the 1970s, but we can also credit Vera Rubin for redefining what a scientist looks like. Now, Rubin set out to study the motion of stars in galaxies. And what you would expect is that the faster the stars are moving and swirling around a galaxy, the more force you need, the more gravity you need to hold them in, to keep them bound, to prevent them from flying out. So what she expected, what she hypothesized that she would see, that the stars at the edge of the galaxy would be rotating more slowly than the stars at the center, kind of like the idea you have for our solar system, where stars nearer to the sun, the planets nearer the sun, would feel more of the gravitational pull from the sun, so they would have more force and be able to move faster than stars at the edge. So what she expected to see, for the more astute who I'll try to walk through this plot, is the dashed line, that the speed of the galaxies would fall off as you go further out in the galaxy. And what she found was quite different. It's the yellow and the blue data points. So what she observed was that all the stars were traveling more quickly than she would have expected. So you can count up all of the stars in your galaxy and deduce the total visible mass, and then work out how much gravity that mass would produce. And so what she saw was that there was no way that the stars would create enough gravity to control their velocities, to be able to hold them into this galaxy. And that must mean only one thing, which was that there was more mass in the galaxy than we could see, more mass than the visible stars. And that's what we call dark matter today. So it doesn't emit or absorb light. We can't see it, whether you're looking with microwaves or UV or optical. But we know that it's there. We know that the dark matter is there from the effect it has on things we can see. So without the dark matter, these stars simply would not be able to remain in the galaxy's orbit. Now, we now know that dark matter comprises of more than 3/4 of all the mass in almost all galaxies. And what we know is that it forms this much bigger, stable halo indicated by the blue in this picture, that encapsulates the much smaller visible galaxy. So what we see of the galaxy is much smaller than the dark matter halo, the dark matter bubble that it lives in. And thanks to gravity, the dark matter creates enough mass to act like a glue to keep all the stars together. And in that way, dark matter is really the building blocks for galaxies and for structure in our universe. And it's such an important finding, and one that we really weren't expecting. Now, the last example I'll give before we really get started came, another couple decades onwards, when humans' minds were boggled by the Hubble Deep Field, this exquisite image here. And Hubble Space Telescope was launched into space to take images of our universe. And this instrument, you can imagine, was in high demand. Everybody wanted to make their observations with Hubble. And applying for Hubble Space Telescope time is extremely competitive. But the director has special discretionary time. So he can decide for some fraction of the time what he points the telescope at. And people must have thought that he was bonkers, because he insisted that he would use Hubble Space Telescope to look at nothing. So he picked a patch of sky where there was nothing there, as far as we could tell, as far as we could see, and just let Hubble keep pointing at it and taking images for 10 days straight. For over 100 hours over 10 days. This teeny patch of sky near the Big Dipper's handle, which is just the size of a pinprick when you hold it up to the sky. And this is what they found. So the Hubble Space Telescope peered and collected enough light slowly over that time to build up a deeper and deeper image until we saw that, the universe was teeming with galaxies in that tiny area. And really, it was another point in time where we had to kind of step back and rethink what we knew about how many galaxies there are in our universe and how big our universe really is. And when we now know that there are about 100 billion galaxies, and our Milky Way is just one of them. So time and time again, the universe has surprised us. So none of these ideas were expected. They weren't really accepted easily sometimes, and sometimes they even came with wild resistance. But slowly, through the power of science and peer-reviewed research, they were proven to be true. And so I've hopefully convinced you with these 3 examples that you have to keep an open mind when you're thinking about the universe, and you really have to trust what the data is telling you, even though it might not be what you expected. And so here is one more story, one that I'm currently working on, and I secretly hope it ends up like the other ones, where we find results that they force us to sit back and think a little bit harder what we think we know. But before we get there, let's just recap what we know about our universe already. So we know that 13.8 billion years ago, our universe was just a hot, dense soup of particles. There were very, very tiny density fluctuations or temperature fluctuations in these particles, just governed by quantum physics. They were totally random. So what does that mean? In this soup of particles, some of them were moving slightly faster than others that were moving slightly slower. Or because of that, some of them might have been slightly hotter and some of them very slightly colder, just by random chance. And then there was this period of rapid expansion, and it left an imprint of those random fluctuations at the time. And we can observe these random fluctuations in the cosmic microwave background. So this is what we call the first light of the universe, and we can observe it. So the cosmic microwave background, there's a snippet of the map now shown in the bottom left. It reveals the differences in color there reveal very tiny fluctuations in the temperature of the background of the light at that time. And this is the earliest light that we can capture in our universe. So the Planck satellite was launched into space, another one, and it allowed us to peer back at that first light and delivered this map to us in exquisite resolution and detail. And this is really the gold standard experiment of our field, this map of the cosmic microwave background. We can use the map to make measurements, and the measurements are they are excellently described by our standard model of cosmology. So we can make all kinds of measurements about how the temperatures fluctuate on that map, and we can predict them pretty much perfectly by our standard model of cosmology. So the cosmic microwave background and these observations by Planck are really some of the best evidence that our standard model of cosmology is a very good one. Now, we know that the expansion of the universe marched on, and these very tiny density fluctuations cooled and expanded such that they seeded the large-scale structures that we observe today. So the random pattern that was in the cosmic microwave background at that time can be mapped to the pattern that we observe in our universe today. Perhaps the slightly hotter particles were able to form clumps sooner, and they now exist as the largest galaxy clusters in our universe. And the more cold areas would be the voids in our universe. So it's the same pattern in our sky. Just to walk you through this, so time is going this way as the universe evolves, and then we have our telescopes at this end, and we're looking back in time when we look at the cosmic microwave background. So we have this structure, this random fluctuations that's kind of evolved into this huge differences in structure in galaxies and galaxy clusters and galaxy voids. And using our standard model, we can replicate our universe and the universe's evolution in computer simulations, like a snippet shown here on the right-hand side. And these 2 pictures both capture our universe. This is our universe. They are just at very, very different time and different stages in the universe's evolution. And it is pretty astonishing that we can describe that evolution with our standard model over 13.8 billion years, from soup of particles to galaxy clusters and galaxy and voids of structure. And it's a very simple model. This is what's, I think, most peculiar to me. We can use just 6 parameters to describe the evolution of our universe with this model. That's all we need to know, 6 numbers, and we can tell you how our galaxy evolved. So it's a very simple model that describes the evolution of our universe. And And what's the catch then? What's wrong? Well, in this standard model, there are three main components. So everything that we know, the stars, the planets, gases, you, me, galaxies, they make up about 5% of everything. The things that we're used to, this normal matter, baryonic matter, it is just 5% of everything in the universe. The rest of it, about a quarter is dark matter, and about 2/3 is dark energy. I'm only going to focus on dark matter in this talk. Dark energy is very different. Now, it's really quite remarkable that in our very insignificant amount of time that we have as humans in the grand story of the universe, that we've honed this standard model, and we can make all kinds of observations that always fit this model. So whether we measure the cosmic microwave background or exploding stars like supernova, or we can map the velocities of galaxies in our universe, or look at the rotation curves of stars. All of these very different observations are well described by our standard model. It is an undeniable success story. And yet the elephant in the room is that at its core, these things like dark matter that we really don't know anything about. And so it's a pretty awkward situation when you're trying to sell that you know what you're doing in cosmology, because we have this extremely successful model, but we don't understand the pillars of the model, dark matter being one of them. And so what that means is we really don't understand most of our universe. And our instruments and our techniques, we keep getting better as technology advances, and we make more precise measurements. We can do our measurements and our experiments better. And so we keep throwing our measurements at this model, at this successful model. And I think we're all kind of hoping that we start to see bigger cracks, and they will guide us as clues to what dark matter is, or what we need to do to change our model so that we can better understand what's happening. Now, we also know that our universe is a cosmic web. So this is, again, that computer simulation that was made at SLAC and Stanford. And the black here indicates the dark matter, and the yellow indicates the luminous matter, the galaxies, the stars that we can see. And what we can see is that the dark matter forms these filaments, this web-like structure. There are nodes and clusters, and then there are regions that have not that much luminous matter. And in the simulation shown here, which does a good job at describing our universe, it's kind of as if the galaxies are like Christmas lights or fairy lights, and they wrap around this invisible scaffolding that is the dark matter. So the dark matter kind of guides where the galaxies live. And so we know from what we're seeing is that dark matter does a really crucial job in our universe. It holds galaxies together. It's the building blocks for our universe. It forms the structure. But, we still don't know what it is. Now, dark matter might seem kind of like something that we made up. And it might even seem that it's, even if not that, that's something that we just don't really need to care about here on Earth. But the truth is, without dark matter, our universe just would not exist. It would not evolve the way we see it today. So here, I'm going to show you two snapshots from a computer simulation. And they're both going to be two different universes with different amounts of dark matter. And this one is really like our universe. It has the amount of dark matter that we think there is, and we set it off to evolve. And what we see is that lots of structure forms, that web forms. And in that universe, you get lots of galaxies. It's very easy in that universe to make a galaxy like our own. The other one has very little dark matter. And when it evolves, not that much seems to happen in this computer simulation. The things that start out like small clumps, they stay very small. So in this universe, you don't really get galaxies like our Milky Way forming, and you wouldn't get the sun and you wouldn't get us. So our home, our cozy home, simply would not exist in a universe with different amounts or with little or no dark matter. So what I'm trying to say is that our universe was kind of concocted with the most precise recipe. You needed a specific amount of dark matter, a specific amount of other things, and in order for us to see the structure that we observe today. There's no room for recipe replacements in our universe. So we need dark matter to build our universe. It's extremely important for it to be able to form structures. And we know it exists because we can see the impact on things that we can see. So what is it? Well, there are a range of models on the market. Particle physicists are on the hunt for a dark matter particle. They have all these fascinating experiments, either underground or with xenon or all kinds of things. And the bottom line is that they haven't found a dark matter particle yet. So we have pretty good guesses, educated guesses for what we're looking for, and the fact remains that it hasn't been detected. Now, cosmologists tackle this from the other side, from a different angle. So we make observations of our universe, and we use them to try to better understand the properties of dark matter. So we can narrow down what our model should look like, what kind of thing we should be looking for. And this illustration kind of shows that there are more models than I can count on the market, and they have all kinds of ridiculous names. There's wimpy dark matter, macho dark matter, fuzzy dark matter. If you can think of a ridiculous name, there probably is a dark matter model for it. But the problem is that none of them really fit the bill. It's not really clear that any of them will work. As a cosmologist, we can tell you where the dark matter is. We know that it behaves like normal matter with respect to gravity. So it has a mass and it responds to gravity, but it doesn't interact with light and it doesn't interact with other matter. So we think that there would be dark matter particles in this room and they would fly right through us and we don't see them. So how do you learn about it? How do you learn about something that is invisible and you can't feel it? Well, one answer is weak gravitational lensing, and that's where I come in. So if you imagine a faraway galaxy, and like Einstein's theory of gravity says, as its light path travels towards us, backtrack, there are things with mass in our universe, like, for example, a massive galaxy cluster, this gray blob, and it is distorting the fabric of our universe according to Einstein's theory of gravity, of general relativity. Now, that means that the light from these background galaxies, their light path indicated by the arrows, gets bent because of the massive structures in the universe. So their light path isn't straight anymore. And what that means is that every image we take of a faraway galaxy is slightly distorted. The light has been stretched and wiggles along a complicated path as it travels all the way to our telescopes. Galaxies whose lights travel past similar structures in the universe, where they have a similar path, what we observe is that they get aligned with each other. So like these two galaxies on the left-hand side, they've passed by similar structures, and we observe that they get stretched in a similar way, and they start to align with each other. So we can start to pick up patterns in the way the galaxies are distributed in our night sky. And the way lensing works is that if we can measure to very accurate and high precision the distortions in these shapes of the galaxies, then it gives us a chance to learn about all of the stuff that the light passed through. So if we see that lots of the galaxies are bent in the same way on one patch of sky, we know that they probably had a lot of lensing, so they passed by some big, massive structures in our universe. I'll show you that in a different way. This is an image from James Webb, looking again at that deep field that we saw with Hubble, but now in a lot more beautiful resolution. And what you can start to pick up when you look at this long enough is these distortions that are very visible here. There is a circular pattern around the center of the image. And what James Webb is looking at is a giant galaxy cluster, and it has lensed the images of galaxies in the background. So these arc-like patterns are galaxies' lights that have been stretched because of the presence of this massive galaxy cluster. And you can do this at home with a wine glass. You move the wine glass forwards and backwards, and you see this lensing effect. It's the same way our glasses work as well, our eyeglasses. And so this effect here is strong lensing. We can see distortions. That galaxy doesn't look actually that bent. What I do is weak lensing, and the distortions that we're working with in weak lensing, you cannot see with your eye. You can't detect lensing on a single galaxy. You need enormous samples of galaxies so that you can pull out very tiny patterns, statistical patterns in the data. Now, we use weak lensing to tell us where the dark matter is, where the mass is in the universe. So for example, here we can tell you that there is a galaxy cluster sitting in front of these galaxies, and there is a lot of mass there. So it's like your eyes can only see light, and then dark matter, weak lensing lets you put on these special glasses, and now you can see the dark matter. It's an extremely powerful probe, weak lensing. It's very unique in the way that it works. And the biggest experiment doing weak lensing right now is the dark energy survey. So here it is. Now the naming is confusing because today we're talking about dark matter. Our survey also studies dark energy, but for our purposes today, let's just pretend it's the dark matter survey. Now I lead the main team in this collaboration, the weak lensing team, and we have scanned 1/8 of our night sky for over 6 years, taking images very slowly and surely, building up this data set. And we've harnessed this information over the 6 years so that we can build a deeper and deeper image of our night sky. We keep looping over the same area. My team comprises of scientists from all around the world, so we can no longer portray science as just a lone man scribbling over his parchment. These groundbreaking experiments will change our understanding of the field, and it requires teamwork from a large group of people. And together we released the results from the first half of the data set already, from 3 years of data. And it is the state of the art in the field right now. So we took data for 3 years, took images for 3 years, and then we spent another about 3 years tinkering over the images, making measurements, calibrating our measurements. And in the end, we cataloged more than 100 million galaxies. So our data set has 100 million good galaxies. We have about 600 million objects in total, but the galaxies, the images that pass all our criteria and are good enough for science, there's 100 million galaxies in there. And that's 4 times more than the previous weak lensing experiment. So we really are an enormous data set for the first time. And this is what we're trying to do. This is the name of the game. So we compare the observations that we make, which is of our universe that has galaxies and has structure, our present day universe, to the measurements, to the model that is so well described by the cosmic microwave background. So we talked about our standard model. It has some of the best evidence of that model come from the observations of the cosmic microwave background from Planck. And when we compare our observations, we set up this very beautiful end-to-end test. And so we're saying, if this model does such a good job at describing the seeds of our universe, can it also describe the vast structures that formed 13.8 billion years later? So we were testing our model over cosmic time by comparing our measurements. And another way of saying that is, does our model that describes our soup of particles very well, does it also describe our universe now that it's teeming with galaxies, with dark matter, a very different universe? Can it describe that as well? Now, it's a particularly exciting time for cosmology because, let me set the scene for you. Technology has rapidly grown, and so we have better experiments, more powerful telescopes, and there are now several teams that are working independently doing weak lensing. We don't really talk to each other when we're doing our analyses, and we're in different parts of the world. And we use much larger data sets than people have ever used before. And what we're desperate to see is, does this model fit our observations? Or perhaps are we starting to see cracks in the picture? And our results are strange. So these are some of the headlines that we've seen. They're not quite what we'd expect. So my first thought was, oh God, I've done something wrong. But no, this is a team effort, and we are a team that we can rely on each other. So it is intriguing that we're finding something strange. It's so intriguing that we're spending another 3 years working on the other half of the data set, and I think we'll be done in about a year's time. Now, what's exciting is that we see similar results from the other teams as well. We're not alone in this. So the other experiments on Sky around the world, they get consistent results with us. We also see hints that maybe our standard model isn't quite right. And that's not a crazy thought. As I said, our standard model does a good job, but we understand 5% of our universe. So surely there's room for improvement. So maybe our results are pointing to the missing piece of the model. Maybe it's some new property of dark matter that we need in our model. Maybe we're on the cusp of the next scientific breakthrough. But I'm getting way ahead of myself, so let me backtrack. So it's Christmas Day, and I'm on a short flight over the mountainous Coquimbo region after a much longer flight to Santiago, Chile. And it is a very rickety ride from La Serena all the way up the mountain to Cerro Tololo. And you're in a van on a dirt road, and you're just slowly winding the dusty tracks until you get 2,200 meters up to the summit of Cerro Tololo. And every corner is more exciting than the last. I know what we're doing and I know what's to come. And up there, it is high, it is dry, and it is smack bang in the middle of nowhere. And that is exactly what we want for an observing site. This desolate patch of land is one of the best observing sites in the world. Now, for astronomers, this is no secret. So when you get to the top of the mountain, there are domes everywhere. And when you look further afield, there's basically nothing as far as your eyes can see. At the summit, this barren land looks like another planet. There are eerie colors, it's sweltering in the day. There are UV signs posted everywhere telling you to cover up or wear sunblock. And our man-made domes are just kind of scattered along the mountaintop. And it really does feel like, this must be what it will be like on Mars in however many years. It really does feel like another planet. And there's so many domes around, as you saw, but they all pale in comparison. This is the Victor Blanco telescope, and it is the king of the mountain. It stands at the very top, and it is simply the tallest and the most gigantic. And it is home to the Dark Energy Survey. So nestled on the 4th story of the dome is our dark energy camera and our 4-meter primary mirror. And telescopes run under the basic principle that if you put a bigger bucket of water into the rain, you'll collect more rainwater. So if we have a bigger mirror, then we're collecting more light at any given time, and these light particles have traveled across the universe through our atmosphere only to land in our telescope. Now, in our telescope is the dark energy camera, which is also huge. So that's me down there looking up at it. So the camera is about 3.5 feet. It has 72 CCD chips. Sorry, 74 CCD chips. So this display here, each one of them is its own CCD chip of our camera. And in total, we have about 570 megapixels. And it's super high maintenance. So it requires a constant stream of liquid nitrogen to be kept at a healthy -100 degrees Celsius. But it's worth it because this piece of kit allows us to image a patch of sky every time we point that's 14 times the size of the full moon. So every time we point, we get a really beautiful high resolution image that's 14 times the size of the full moon. Now, we're there to work, and that means it's a race against the sun. So as soon as the sun sets, you try to get as much data as possible before the morning light starts to creep in and you have to pack up and go to bed. But observing life is pretty special. So there's an afternoon meeting up at the camera, up at the telescope, where you make the plan for the night, the OBS plan. Then you head back down to the lodge and get some dinner. And then you trek back up to the mountaintop again. And once things are ready to go and there's no problems or that nothing's broken in the telescope, then all of the astronomers from their domes emerge at sunset to watch the sun go down over the horizon. The sunset is pretty spectacular, and this is a well-established tradition at the mountaintop. And what's incredible to me is that humans are not the only one who've noticed this. So these visachas, or kind of kanga rabbits, somehow, they live on Cerro Tololo, and they also emerge to watch the sunset every night. So it is, I did not believe it until I saw it, but every night at sundown, astronomers and visachas are wide-eyed facing west. The noticeable quiet of the mountaintop is broken a few hours before sunset as all of the domes, I hope you can see this well, creak open. And they all start rotating over the night throughout the night sky. And they're kind of like guardians of the sky, these telescopes. They're perched on the summit, they creak open their eye, their dome, and they start turning around and doing their work throughout the night. And we just, they rotate slowly, taking all the images, and we just have these little headlamps, and we kind of creep around them, trying to learn what we can from the universe. And our camera, our dark energy survey, can do all kinds of cool things. So this is, if you've lost your Tesla, like Elon Musk, we can detect it in our images. So there it was, 3.5 million kilometers away when the Tesla was launched into space. I don't know why, but we could find it in our images. And if there's an earthquake the night before, we can surely see that in our images as well. I'm really glad I was not doing that observing run at the top of Cerro Tololo. But what we're really after is galaxies. So this is a processed image, a processed and stacked image from our camera. So this is the pattern of the 74 CCD chips. And remember, 14 full moons can fit in this. And And on a full night of observations, we can take about 150 exposures and we stack some of them. And if you do the math, if you have good weather over the night, then we can image in every night about 1 million galaxies for our experiment in just one night. And you know, when you zoom in, this doesn't look so remarkable, and these probably look like stars, but when you zoom into this image, each of them is some spectacular galaxy in high resolution that probably no one else has ever looked at before. So it really is quite cool to play with the images as they come in the night. Now, here are some particularly big, beautiful DES galaxies. So you can see they really come in all different shapes and sizes. And to do our analysis, to do weak lensing and to learn about dark matter, we need 3 pieces of information. So we need the positions of the galaxies on the sky. We need an estimate of their shapes. So we measure their ellipticities. And we also need to know how far away we think the galaxies are. So a measure of the distance to the galaxy. And, you know, I started my PhD and I was like, this doesn't really sound so bad. We can measure shapes and distances. How bad can it be? But the problem is that the galaxies that we're dealing with aren't these big, beautiful galaxies. We want the distances and the shapes of these ones, which are just the fuzzy blobs in the background. They are further away and they have been lensed more. And our challenge gets harder because we have this beautiful galaxy and its light particles, you know, allow us to see its structure, and they travel all the way across the universe and they get lensed and they carry this signature that we're after that can tell us about dark matter until they get to Earth, these light particles. And then our atmosphere just totally ruins our images. So the atmosphere will smear. This is the lens effect happening. So you see it get a bit stretched. When it gets to Earth, the image will get totally blurred and smeared due to our atmosphere and due to the telescope imperfections. Our detectors are not perfect, so they measure a pixelated image. So we now have something that looks like that. And then there's noise. So in the end, we have a galaxy that looks like that. And you know, measuring the shape and the distances to those is a bit more tricky. And even that's probably a really nice one for our experiment. And the problem gets even worse than that, because now we think we can do it perfectly. Measuring the shapes of these galaxies isn't so bad. So one fuzzy blob we can handle, but many fuzzy blobs become tricky. So what's happening now is that our telescope images, our technology has grown so much that when we take an image, it's much deeper. It allows us to look further back in space. And so when you're looking at a galaxy, it's probably overlaid on another galaxy along the line of sight. And what that means is that every time, you can see them better, but there are tiny little galaxies there. Every time we try to measure the lights of this little galaxy, we're probably getting lights from about 5 other galaxies nearby, creeping into that pixel. So it really starts to get challenging to measure the shapes and distances to those galaxies. Now, I spend so much of my time thinking about how to measure galaxies and working with them. And the truth is, I don't like galaxies. I really don't like them. They are just pawns in our analysis, because what we're after is dark matter. And we just use them to tell us about the dark matter. So this here is a map of the largest dark matter map ever made. So this is our footprint on the sky that we measure with the Dark Energy Survey. This map, if you've not seen this before, it's like how our globe is round. And when we put it onto 1D, you get this shape. We're doing the same thing, but looking out instead of down. And so the Milky Way is stretched horizontally the way we see it, but it looks like that the way you project the image. And this is our footprint here. So this small Magellanic Cloud and large Magellanic Cloud. And the DES survey has this weird, people say it's a tank. I think it looks a bit like a hummingbird. It has this weird footprint on the sky. And in our map, the lightest bits here, the more yellow bits, will be the places that have the most dark matter. So we saw the most lensing in that area. And the darkest bits are where we have the least dark matter. They're more devoid of dark matter. So we can make these maps, but it's not just about making pretty pictures. We make measurements of the shapes of the galaxies and work out their statistical patterns. And our pipeline is like an industrial machine. We crunch the numbers and we compare the measurements to what we would predict from our standard model of cosmology. So our pipelines do a Bayesian analysis, if for any math folks in the room. And they continuously compare these measurements to a different prediction of our universe until it finds the best fit. Does it fit our standard model? And in this kind of statistical analysis, we get these numbers out and we compare them to the numbers that the cosmic microwave background predicts, those 6 numbers that describe our universe. So we have a standard model, 6 numbers. The cosmic microwave background says these 6 numbers are these values. And then we compare the values that we get to those, to what they get. And that's how we compare our results, basically. Now, I'll walk you through what we found. And these are the real measurements now. So don't worry about the plot, we'll walk through it. So on the y-axis, I'm showing the value for one of the parameters. And it tells you how much structure, how much clumpy matter there is in our universe. And the values that we get from the cosmic microwave background, that gold standard of our field, is shown by the yellow band in this plot. Now, what happens when we add in the weak lensing data points? So these are from different experiments, not the dark energy survey. This is what the field looked like before we released our results. And what we can see is that, they're all on one side of the cosmic microwave background measurements. So what we would expect is that if the orange bar was the model, you would expect that you wouldn't always get the exact same value, but you would have, sometimes you would get values higher than the model, sometimes lower than the model. The measurements should fluctuate around the model. And so it's been quite strange that we keep seeing all the weak lensing measurements coming out low compared to what the cosmic microwave background predicts. So we want a less clumpy universe. We see a less clumpy universe than what the cosmic microwave background, what our standard model dictates. And that's really quite compelling. And what's more strange is that none of these data points disagree with the orange data point to some huge significance, but it's this persistent trend that everybody is low. Why does that happen? And this lowness has existed from every weak lensing data set to date. So these are just showing the most recent values. And as time has passed, people have typically asked when you present your measurements over the last 10 years, well, what have you done wrong? Particularly members of the orange bar team. What did you do wrong? Why aren't you getting the same values that we got? And at first, I think that was fair because it was a new technique that we're using, and we really needed time to hone our models and hone our methods. And weak lensing data, as you saw, is really challenging to wrangle with. It's very difficult to make these to pick up this tiny signal in our measurements. But now I think we've really honed our methods, and we have 3 independent teams doing things without talking to each other. So it's really hard to ignore the evidence on the table. Now, in the dark energy survey, we knew because of the landscape of the field and because we had this enormous data set that there would be a lot of scrutiny on our measurements. And so we were very careful. And one thing that's important to tell you is how we did our experiment. So we know that as humans, we are biased. I'm a young scientist. I'm relatively new to the field. It might be that I just don't want to disagree with the state of the art. I don't really want to disagree with the gold standard of our field. I might just really, really hope that our experiment comes out smack bang on top of what the cosmic microwave background predicts for a more peaceful life. But that kind of human bias is not good in science. We're supposed to be objective. And so to get around that, we did our entire analysis for 3 years using fake data. So no one could touch the real data for the entire time. And we do all our calibrations and anything, we have to make so many decisions of, is this model better? Is this model better? Should we calibrate this way or this way? So all of these subjective decisions could be made without knowing where our data was going to sit. We wouldn't know which way we were turning the dials, essentially. And then we hit go on the real data on the pipeline. We get our entire collaboration, which is about 200 to 300 scientists on a call. And then we look at the results with everyone all together. So it's one of the most important presentations of your career, and you have absolutely no idea what you're going to see in the results. So definitely led to a lot of nightmares in the run-up. But it's all for the sake of unbiased science, so it is important. And this is what we found, this green bar. So we used 100 million galaxies, the most powerful data set to date. And again, we found some measurements that is low compared to what the early universe predicts. Here we are again. And in cosmology, we call this now a tension. It's not quite a disagreement because we're not at 5 sigma. There's not a huge difference between our values, but it is a tension. It is intriguing. Why do we all keep finding this disagreement, this slight disagreement with the cosmic microwave background? What does it all mean? Well, there are 3 options. Option number 1 is that something's not quite right in the Planck cosmic microwave background measurements. But as I said, this is the gold standard of the field, so I'm just not going to put that one on the table right now. And that's just joking around. The measurements from the cosmic microwave background are just such a good fit to the standard model that it is very hard to move their results around. It's hard to see how there could be a mistake there. Option number 2, we're doing something wrong in our weak lensing measurements. But we have 3 teams that are working independently, so we'd all have to be doing the thing wrong. And that would be hard. That is quite hard to imagine what that would be. And option number 3, that this is showing that our standard model isn't quite right. We're seeing the cracks. We need some modification to our model, some new dark matter property that can reconcile the difference between these 2 experiments. Now, there are many voices in my head when we see this plot. Is it so bold to think that there's something wrong with our standard model? Well, let's just dial up the imposter syndrome. I mean, who are we, these new, relatively young fields, to come out and say, it's totally wrong, we need a new dark matter model. But on the other hand, as we talked about at the start, cosmology has this habit of turning our views upside down and defying our expectations. And right now, this decade that we're in is the first time that we're kind of just drowned in data. We have so much data from our technological advancements that it is the time to make discoveries. It will be the time that our model starts showing cracks. So what do we do with that? Well, I moved to Cambridge a year and a half ago, and George Estafew I started working with, and he led that orange bar, the Planck experiment. So the first few months that I was there, we argued intensely about whose experiment was wrong. It was really very fun. I'm only joking about it, but we disagreed on what about you this? Why didn't you consider this? Why did you choose to do this? Why would you do that? Until in the end, a few months in, we decided, okay, I'll believe your results. I believe them. I can't see what's wrong. And you trust my results. What could this mean? What could this tension mean? And we proposed in a paper last year that, maybe this is a smoking gun, potentially for some new dark matter property, and what those properties would look like. And the problem is, I say potential solution because with weak lensing, it's very hard to know. One trouble that we're having is that we need to model the impact of galaxies in our measurements. You have to care about galaxies for some reason. So galaxies have these explosive things happening, these jets that spew out energy, energetic jets that spew out energy, and they impact our measurements. They impact our model. Rather. And so it could be that what we're seeing is some new property of dark matter, but it also could be that we don't know how to model galaxies well enough. And we do a thorough job with modeling them. There are complex simulations, hydrodynamical simulations that can build galaxies, and they fit with lots of our observations. So what that would mean is that all of those simulations would have to be wrong. So the quest that we're on now, we've hired 2 PhD students, Lee and Calvin, and we are trying to decipher these 2 things that look like each other. Do we understand how to model galaxies, or are we looking at some new crack, some new property of dark matter? Now, it won't end with a dark energy survey. As I said, right now, we're doing the second half of our analysis. So now we'll have the full 6 years of data, and we're working hard on that. But really, we're just the training ground for what to come. This also isn't showing up, but this is a view of the night sky from the dark energy survey camera, standing right next to it. And one mountaintop over, right on the horizon, is the Reuben Observatory. Maybe it shows up on this one. Anyway, you can see it online. So the Reuben Observatory will switch on in about a year's time, and it will be a total game changer for our field. So what it plans to do is to span our entire southern hemisphere. So if you're in the southern hemisphere, the entire night sky, over and over, it will span the night sky every 3 days. And it will do that for 10 years until we build up this deeper and deeper image of our universe, a movie of our universe, essentially, and how it's evolving over 10 years' time. In just the first year of data, we will have 10 times more galaxies in our analysis, we think. So we'll be up to 1 billion galaxies in our analysis. And we're really just, as I said, we really are just the training ground. We are desperately trying to make our methods bulletproof enough so that we can handle this amount of data that's hitting us. It's not just about Reuben as well. Euclid Space Telescope will launch this summer now. They'll do the same weak lensing measurements, but from space. So they'll have less data, but much higher resolution. They won't have to worry about the Earth's atmosphere smearing your images. And then Nancy Grace Roman's Space Telescope will launch in about 5 years or so. So it's no doubt that the field is going to change. And with these advancements in technology, it genuinely is hard to think about what our model will look like in a decade's time. What will our measurements say? What will change? We are about to be totally spoiled with data. We'll have so much data that what I'm excited about is kind of cutting up that data, not just doing our standard analysis anymore, but looking for weird objects and doing your analysis with the weird objects. So we can pick out the galaxy clusters. We can look for tiny dwarf galaxies like the Small and Large Magellanic Clouds. We can look for them in our data, and we'll be able to learn new parts about our standard model from these weird objects. Now, the standard model has been standard for a couple of decades, but we are at the dawn of something new, and I can't wait to see how our model and our understanding changes. One thing is for certain is that we won't always only understand 5% of our universe. We will get better. And there'll be new young scientists that will bring the next paradigm shift for our understanding. Even then, I'm sure there will be more pieces of the puzzle to solve. So keep looking up and keep asking questions. Thank you.
What's your pet idea for what dark matter and dark energy are? You have that lovely supermarket.
Yeah. I think what I think is that we don't have the model that it will be the correct one is not on the market yet, in my opinion. I think none of them really work. A few of them look promising for this potential solution that we proposed. So what we proposed is that matter in the universe needs to be redistributed, especially on small scales, to be able to reconcile both the observations. And things like axions or self-interacting dark matter, they would all have this effect. So they would fit the bill for what we're proposing. But I think that the exact model probably, it's probably, we're really far from it. And what's more intriguing is that people ask this question as if there's going to be one type of dark matter particle, and we don't really know that either. That's just the easiest thing that we can do. So yeah, I think the floor is wide open.
So it's a message for anybody considering a career in this.
Yeah.
Okay, questions from the room. I'll go over here first of all.
If I'm allowed to, the first one was that there have been some results sort of given out that there might be matter that we haven't really detected in the disk, which of galaxies, and that would sort of give you an explanation for the 1/r distribution of mass that you get from galactic rotations. And the second one was how does your S8 relate to the Hubble constant discrepancy that's come up from?
Okay, so first question is, I haven't seen this about the evidence in the disk, but I guess that would be alluding to maybe we don't need dark matter. Yeah, I think we have very clear evidence that dark matter exists in galaxies. Lensing is very special because it kind of shows you exactly where the mass is without needing to know what the mass is, whether it's dark matter or normal matter. And so we know, for example, when we do lensing of our galaxies, you can get the profile of mass. And for the light that you can see, it would be this very not extended profile. But for what we can see from our lensing is there's this huge halo around it. There is mass all around it. So I think we have really solid evidence, not just from lensing, that matter exists. On the second question, that's very astute. So there's another tension in cosmology right now, which I think is making it more exciting. So there's the Hubble tension measurements on the expansion rate of the universe. And that one's a bit more popular, right? They have a higher significance of attention, about 5 sigma, whereas all of our measurements are about 3 sigma, but we have them from multiple sources. So they're a bit different in that way. And the problem is that they go in opposite directions. So people keep proposing new models that can explain one and it makes the other one worse. And so what does that mean? It could mean, well, are we wrong to think that we need one fix for 2 things, that we're only one step away from the correct model from our universe? That would be a bit arrogant thinking given where we are. Or it could be that one of the tension goes away because we start learning how to do our measurements better, or something. So yeah, it's really compelling that we're seeing 2 sets of cracks. And it's intriguing that they don't help each other. It's really hard to solve both at once.
I was just wondering, what's the current assessment of MOND as an alternative explanation for dark matter?
Yeah, this question every time. I think there's pretty clear evidence, in my opinion, that MOND is off the table.
We should probably say what
So
MOND
this is an idea of a theory where we don't really need dark matter in this theory. You do need other things. So you need something like neutrinos to have a mass, or so you get kind of like it's replacing the magical thing that we need with another magical thing, which is not really, we don't really have evidence for that. But there are many observations that we can make. So most famously, the bullet cluster, which tell us that dark matter is there, and tells us a lot about the properties of dark matter that we need. So yeah, it's not a model that I consider seriously in my experiments.
We have an online question from David Partridge. Do you have an opinion on the apparent link between dark energy and the anomalous growth of supermassive black holes as announced by the University of Hawaii last month?
Yes. So there was a paper in the last month that said that maybe we didn't talk about dark energy today. Let me maybe do 1 minute on that. So dark matter holds things together. It holds our galaxies together. It forms the structure in the universe. Dark energy basically does the opposite. So it pulls your galaxies further and further apart. It doesn't rip up the galaxies, but it puts more distance between the galaxies. So if I was an ant on a balloon and the balloon was inflating, it's if you have two ants, they'll now move further apart from each other. That's how dark energy is expanding our universe. And there was a paper that said maybe dark energy was due to black holes. And I think that would be a really hard thing to justify. I think it invoked quite a lot of discussion in the field. And it is really hard to think that something that's astrophysical, that is very localized, would impact, the entire model of the universe. It's quite a weird link to make and to prove.
A chap called Aryan Shejal. There's, in addition to thanks for an excellent talk, how does one compare CMB and DM divided by DE distribution if the CMB occurred 13 billion years ago? And what exactly does one measure with the DE camera?
I think we need some explanations of those terms in your answer, actually, Alexandra.
Yeah, I think what the question is trying to ask is how do we compare our measurements to the cosmic microwave background when we have our... so the idea is that we make any measurement that you can think of, not just ours, so supernova, or because we have a standard model that gives us a way to compare our measurements. So we take the fact that the cosmic microwave background is an excellent fit to this model. It gives us evidence for this model. And then when we make our measurements, we try to model them with the same description, with the same model. And you see if you can do that, if you get a good fit. So within the framework of our standard model, you can compare two sets of measurements quite easily, even if the measurements are totally different. So having a model really helps you. It's hard to compare. It's like trying to compare apples and oranges without knowing that they're both fruit. Yeah.
Thank you. I'm going to take one final question. If it's in the room from somebody who hasn't answered a question before, otherwise we'll look and see if there's another one online. Do you have others, Sean? One more then, go on.
I can't pronounce this chap's name. Naira Bioti Kalita. Does dark matter have any contribution to the Hubble constant tension?
Yes, I think that's a similar question to this gentleman asked here. It's really hard to describe both of them with a single fix. So, yeah.
Well, look, I have to say, absolutely phenomenal lecture, really very much appreciated. And you can see from the turnout you've got here in the room and online just how well this has gone down and the caliber of the questions. Well.
Yeah.
So thank you once again. We very much appreciate you coming here today. Thank you so much.